So the last thing we're going to talk about for carboxylic acid derivatives is the spectroscopy of them. And the spectroscopy of carboxylic derivatives is not much different than what we've seen before. Um, like most IR active materials, especially anything with a carbonyl, it's the carbonyl peak that is most indicative of the um, derivative being there. And the carbonyl peak is affected really by the presence of electron donating or electron withdrawing groups. So these are the same things that determine um, uh, the activity or deactivating characteristics of groups on a aromatic ring, right? So that basically, that kind of shields or pulls electron density away or into the carbonyl bond. And so that affects the frequency, right? So if the bond gets longer, then it has a, smaller frequency. And if the bond gets shorter, based off of electron drilling, this one is going to have a larger frequency, right? So this is how these groups are going to be shifted. There's also proton NMR. And the only thing of relevance for the proton NMR is that the alpha carbon, right? So if this is our carbonyl, this is the alpha carbon right next to it, alpha carbon right next to it if it's a ketone, so on and so forth. The alpha carbon protons are slightly deshielded, so they're going to be shifted um, upfield to higher delta values. And they're going to be around a delta value of around 2 parts per million. So the carbonyl alpha carbons usually have a downshifted, or sorry, upfield peak, right? So they have a stronger response in the NMR. The carbon 13 NMR is a little bit more complicated. The basically the carbonyl carbon absorbs in a different range from around. So the carbonyl carbon absorbs about 17 or 170 ppm to around 201 ppm. And so if I were to kind of give you a list of these, we would have something like acetic acid. It's going to be around 177.3. The ethyl acetate, so that's going to be in ether, to be about 170. The acetyl chloride, that's going to be around 170 as well. Acetamide, that's going to be around 172. Acetic anhydride, that's going to be around 166. And then acetone and acetaldehyde, those are going to be around 205.6 and 201.0 for the ppm. So this is for the carbon 13 NMR spectra. And so those are some of the typical delta values that you'll see for carbon 13. As a lot of these are very close together, it's actually difficult to distinguish between these compounds, right? So they're so close together that it's kind of hard to actually distinguish between these compounds. And then for the IR spectroscopy, we see that this is all looking at the carbonyl peaks, right? And the carbonyl peaks, the specific position is determined by the kind of electron donating or electron withdrawing character. And so if we see that we have a acid anhydride, for example, uh, which will be down here. If I use this as an example, we have effectively some electron density that can be donated to the carbonyl bond from resonances with each carbonyl, and so we see that it's shifted to larger frequencies. Resonance effectively pulls electron density away from the carbonyl bond because it can share then with the anhydride. And although it isn't a major contributing structure, it shortens the carbonyl bond. So the CO bond here gets shorter, and then that makes it move to larger frequencies. Why, if we look at acid chlorides, they also move to slightly larger frequencies. Whereas if we have something like a saturated amide, where we have an electron donating group close by, this is going to move to a smaller frequency. If we look at a disubstituted amide, that'll be even a lower frequency as electron density is added to lengthen that bond. Okay, so that'll wrap it up for derivatives of carbonyl compounds. We talked about spectroscopy. We talked about naming. We talked about specific reactions of carboxylic acids to get to these derivatives, and then also from each of these derivatives to get to other derivatives or other compounds. Next, we'll be talking about alpha carbon substitution, which is important for making carbon-carbon bonds. So starting from smaller molecules and making larger molecules. And we'll talk about some carbonyl condensation reactions after that.